Hello, everybody. I hope you're all doing well and you're ready to continue looking at our 2012 Euclid paper. We are on question number 6 this time. So, still a light bulb and a written question. Blaise and Pierre, which I'm pretty sure it's Blaise Pascal and Pierre de Fermat, or Fermat, will play 6 games of squash. Since they are equally skilled, each is equally likely to win any given game. In squash, there are no ties. The probability that each of them will win 3 of the 6 games is 5/16. What is the probability that Blaise will win more games than Pierre? Okay. So we've got 6 games of squash. The probability each of them wins 3 of the 6 games is 5/16. Now, they're equally skilled, so it's really just a probability of 1/2. Okay, probability of 1/2 that Blaise wins a game, probability of 1/2 that Pierre wins a given game, right? Now, there's a couple ways we could do this question, and since it's a light bulb, we may wish to focus on the shortest way. Okay? Now, since Blaise and Pierre are equally likely to win any given game, there's sort of a symmetry argument that could be made. Okay? So, if we were talking about games that could be played, we could have Blaise wins more than Pierre. Blaise wins the same as Pierre, that's 3 games apiece. Or Blaise wins less than Pierre. But we can't actually tell at a probability level who's more likely, Blaise or Pierre, because on any given game they're equally likely. So any calculation I make for Blaise winning 4 or 5 or 6 games, it's going to be the same calculation for Pierre to win 4 or 5 or 6 games. So if we know there's 5/16 for them to sort of tie the number of games or to have the same number of games played, that leaves, so that's 16 over 16 minus 5 over 16. That leaves 11/16 as the probability that one of them wins more games than the other. But those two numbers, whatever they are, should be equal. Let's not use P because we've got P for Pierre. But those two probabilities should be the same because, well, you can't really tell Blaise and Pierre apart. So we divide by 2, should be 11/32 is the probability that Blaise wins more than Pierre. We don't know how many more, but wins 4 or 5 or 6 of the games. Okay? So that's sort of the shortcut reason your way with a symmetry argument. We could also try and do the direct calculation. Okay? We could try making a probability tree, but with 6 games, that's going to become really annoying very fast. Okay? So what could we do? Well, we could say, well, what's the probability that Blaise wins some number of games, like B games? And depending on how good you are at probability, you might know a very nice, neat formula for this. But imagine we had a probability tree. Okay? Imagine we had a probability tree. And, Blaise wins, Pierre wins. Blaise wins, Pierre wins. Blaise wins, Pierre wins. Blaise wins, Pierre wins. So each branch of this tree tells a little story. Blaise wins the first game, then Pierre wins, then Blaise wins, then maybe Blaise wins again, then Pierre wins, then Blaise wins. Okay? Now, if Blaise wins B games, and we know there are 6 games in total, we're going to have Blaise win B times. Now, what's the probability that Blaise wins? 1/2. Right? Because they're equally skilled. They're equally as likely to win, and there are no ties, so each must win 1/2 the time. Okay? So there will be B games, and so B of these branches will have 1/2 on them. Right? Okay? But the other 6 minus B parts of the branch will be Pierre winning. So we go down a little bit. Okay? And so ultimately, when you work that out, that's just going to be 1/2 to the 6. So any given branch that tells a story, the probability of that particular story, Blaise wins the first round, then Pierre, then Blaise comes back twice, and the probability of that happening is going to be 1/64. Okay, but there are lots of ways for Blaise to win B games. It doesn't have to be in one particular order. Blaze could win a whole bunch of games and then start losing. So how many of the branches on our probability tree will have exactly B Bs, and the remaining 6 minus B nodes are Pierre winning? Okay? So that's where we're going to have to use a little bit of combinatorics. We've got 6 games, and we need to choose B of these games for Blaze to win, and then Pierre will have to win the others. So that's how many branches, and each branch is worth 1/64. Okay? So, using combinatorics, and if you don't know combinatorics, by all means, just use the reasoning argument we did at the start. Okay? That's why I try and show multiple ways to do these contests. But this expression with factorials is the probability that Blaze wins a certain number of games. We can even test this. What is the probability that Blaze wins 3 games and therefore Pierre wins the remaining 3? 6 minus 3 is another 3. And so that's 6 times 5 times 4 times 3 times 2 times 1. 6 and those and those and so you'll get 20 out of 64. Well, divide top and bottom by 4 and you'll get 5 out of 16. The probability that they each win 3 games is 5 out of 16, which they did tell us. Okay? They told us so that we could do that nice little shortcut. But now I'm more interested in Blaze winning 4 games, 5 games, or 6 games, because those are the cases where he wins more. And so if you want to do it computationally, you'll notice this is taking us a lot more time. And so I would really recommend on a contest doing sort of the reasoning argument, the symmetry argument way. It's much faster. But if you're interested in figuring out exact probabilities, you would do something like this. And you'll get 15 over 64, 6 over 64, and finally 1 over 64. And you add those up, and you'll get 22 out of 64. Divide top and bottom by 2. 11 over 32. Again, as we already had, I'm just showing you a different way to do it. This is the way my students in university would do it, because they don't look for shortcuts. They just sort of mindlessly calculate with combinatorics and factorials. And if you don't know those, but you're a little intrigued about how I'm doing all these probabilities, you might want to look up combinatorics. It's a nice thing to know. Okay, if you're not in grade 12, you likely will not have seen this outside of any math enrichment. But combinatorics is very useful, and if you're ever going to do statistics or probability, they're definitely something to know. And they're also useful for counting problems. That's 2 ways to do it, the short way and the long way. But I suspect most people just do the short symmetry argument. Okay, B part. Determine all real values for x, for which, look at this. We got a lot of powers of 2 and a lot of powers of 3. Let's copy this over. 3 to the x plus 2, 2 to the, I think it was x plus 1, x plus 2, and then plus 2x. Is equals 3 to the something. Now equals 2 x plus 5 plus 3 to the x. Okay. So, what have we got here? Powers of 2, powers of 3. I want to collect all my powers of 2 and powers of 3 onto the same side. I'm more comfortable with them like that. So we'll move everything over. Okay. Additionally, I'd like to be able to combine these two. So what I'm going to do is I'm going to take out a factor of 3 to the x over here. And I'll be left with 3 squared minus 1, which you might recognize is 8. Okay. And over here, I'll take out a factor of 2 to the x, and so we'll be left with 32, 2 to the 5, minus 4, minus 1. Oops, this should be a minus sign, which you might recognize as 27. So 3 to the x times 2 to the 3 is 2 to the x times 3 to the 3. There's lots of ways to do this. You could divide both sides by 8 and 27, and you can say, all right, 3 to the x over 3 to the 3 is the same as 2 to the x over 2 to the 3, or 3 to the x minus 3 is 2 to the x minus 3. Okay? But powers of 2 and powers of 3, if they're to the same power, are never the same number, except in exactly one situation, and that's 3 to the 0 is the same as 2 to the 0. Otherwise, as long as it's the same exponent, your power of 3 is so much bigger than your power of 2. Or if it's a negative exponent, your power of 3 is so much smaller than your power of 2. Again, this only works if I'm buying the same exponent. Otherwise, we might have to bust out logarithms or something. But if that's the case, if we've got a power of 2 equal to a power of 3, that means x minus 3 must be 0. So the only one that works is x is equal to 3. Right? That's it. That's all we can do. X must be equal to 3. There's no other tricks or rearrangements or anything we can do. There we go. We could quickly verify that 243 plus 32 plus 8 is the same as 256 plus 27. Right, so that's over here, that becomes 283, and over here, 6 and 7 is 13, carry the 1, 283. But that's the only one that works. So despite the fact that they said all real values, it turns out it's just a little positive integer, but it was important that we show our work there. Okay, so that was question 6, and we can move right along on our Euclid paper to, looks like some geometry problems in question 7.